Hello, in this lecture we'll answer on two questions. In the first question, we find out the area of this semicircle that is inside quarter circle A or B. And in the second question, we'll find out the area of this ring shape that is inside rectangle ABCD. So we start with the first question. So in the drawing, we have quarter circle A or B. We know that side AO of this quarter circle AOB equals to 5 units in its length. That is to say, the radius of this quarter circle AOB is equals to 5 units. And inside this quarter circle AOB we have this semicircle. And our mission is to find out the area of this semicircle. So first of all, we'll define the center of this semicircle. This point is point C. Likewise, we will define the touching point of this semicircle with this quarter circle. This point is point F. We will define the second touching point of the quarter circle with the semicircle. This point is point G. We will define the point of tendency of tangent AO with this semicircle. This point is point H. And finally, we will define the point of tendency of tangent BO with this semicircle. This point is point L. In addition, we will define the radius of this semicircle as X. So CF, that is the radius of the semicircle, equals to X, and the radius CG of this semicircle is also equals to X according to our definition. In the next step, we will join point C and L together by a straight line. CL is of course the radius of this semicircle, that is equals to X. We will join point C and H together by a straight line. CH is also the radius of this semicircle, that is equals to X according to our definition. So here we can implement rule 1, because we have the radius CL is equals to X. The radius CL is drawn to point L, that is the point of tendency of tangent OB with this semicircle. That whenever your radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH that is equals to X. The radius CH of this semicircle is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we can deduce quadrilateral CHOL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CHOL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we will relate to quadrilateral CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL, but CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the sum integral CH-OL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x units in its name. So we actually found out that quadrilateral CH-OL is not a rectangle but a square, one because of the fact that all of its sides are equal to each other, each side of this square is equal to x. In the next step, we join points O and C together by step 9. By joining points O and C, we're going to the right and associated triangle, triangle CLO. In the next step, I'll copy the right and associated triangle, triangle CLO in a new page, and we'll implement the Pythagoras theorem in this right and associated triangle, triangle CLO. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually this is the right in associated triangle, triangle CLO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO square equals to CL square plus LO square. So I write it down. CO square, that is the square of the hypotenuse, is equals to CL square plus LO square. CL is the missing side, CO, the hypotenuse CO is the missing side, so we'll leave it as it is. CO square equals to CL square. CL is x, therefore CL square is x square. Plus LO square. LO is also equals to x, therefore LO square is x square. So in total we actually found out that CO square equals to x square plus x square. X square plus x square is 2x square. So CO square equals to 2x squared. If we take a root out of this equation and finally get that CO, the missing hypotenuse CO, the length of the missing hypotenuse CO is equals to the square root of 2 times x units. So we found out that CO equals to the square root of 2 times x units in its length. Point O is the center of the quarter circle. So from this point that is the center of the quarter circle, we have here line segment OC that bisects chord FG. Again, line segment OC bisects chord FG. Why line segment OC bisects chord FG? Because of the fact that line segment OC divides chord FG into two halves. Each half equals to x. CF equals to x, and the second half CG also equals to x. So line segment OC that is drawn from the center of the circle bisect chord FG. And therefore we can implement here rule 7. So I repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is perpendicular to that chord. So in the drawing we have a circle. This is point O, that is the center of the circle. So from this point O, that is the center of the circle, we have line segment OM that bisects chord AB. That is to say MA equals to MB. So line segment OM divides chord AB into two halves. The first half is MA and the second half is MB. And therefore, according to this rule 7, line segment OM that is drawn from the center of the circle and bisects chord AB, line segment OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have line segment OC that is run from the center of the quarter circle, that is to say from point O. So line segment OC by self code FG. So all the requirements of rule 7 are satisfied, and therefore we can implement rule 7. According to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we will join points O and F together by a straight line. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and then at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, line segment OF is the radius of the quarter circle. We know that the radius of the quarter circle equals to 5. Why? Because OA equals to 5, and OA is the radius of the quarter circle. So OF is the radius of the quarter circle, that is equals to 5 units in its length, according to what is given us the question. So in the next step, I'll copy the right and green triangle CFO in a new page, and we will implement the Pythagoras theorem on this right and green triangle CFO. Here by PT is a version for Pythagoras theorem. So actually, this is the right and green triangle CFO that according to the original drawing, according to the Pythagoras theorem, in this right triangle CFO, FO square, that is the square of the hypotenuse, equals to FC square plus CO square. Again, FO square equals to FC square plus CO square. So I write it down. FO square equals to FC square plus CO square. FO, the hypotenuse FO is 5, therefore FO square is 5 squared, that is 25. And it is equals to FC square. FC is x, therefore FC square is x squared plus CO square. CO is equal to 2 times x, therefore CO square is 2x squared. So in total, 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So if we found out that 25 equals to 3x squared, here we divide this equation by 3, and finally we get that x squared equals to 25 over 3. X squared equals to 25 over 3. Our mission is to find out the area of this semicircle. So what is the area of the semicircle? The area of any semicircle equals to pi times the radius of the semicircle squared divided by 2. The radius of this semicircle is x, therefore the area of this semicircle must be equal to pi x squared over 2. So I write it down. The area of the semicircle, the area that we are looking for in this question, is equals to pi x squared over 2. So it is pi over 2 times x squared. And we just right now found out that x squared equals to 25 over 3. Therefore, we substitute x squared in this equation by 25 over 3. And finally, we get that the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So if you found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of the semicircle equals to 13.09 square units. Repeat again, the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, this equals to 13.09 square units. So we finished with the first question. In the next step, we present to the second question and we'll solve it. Our mission in the second question is to find out the area of this green shape. So, in the drawing, we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD, we have this semicircle and this quarter circle. Repeat again that our mission is to find out the area of this green shape. Our mission is to find out the area of this green shape. So, first of all, we will define the radius of this quarter circle as x. BC is the radius of this quarter circle, and therefore BC equals to x units in its length according to our definition. So I write it down. We will define the center of this semicircle, this point is point O. We know that all the angles inside any rectangle are right angles. Therefore this angle is a right angle. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. So I write it down, DC equals to 5 units in its length. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, and it is equal to x. But AD is not only one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle AD is equals to x. If the diameter equals to x, the radius must be equal to half of it. Therefore, the radius of this semicircle is x over 2. So the radius OA of this semicircle is x over 2 units in its length. And the radius OD is also equals to x over 2 units in its length. So in the drawing, we have an external line between this semicircle and this quarter circle. That is to say, they touch each other externally at this point. We define the touching point, this point, as point S. And whenever you have an external line between two circles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles, and they have an external line between them, and this point, point P. That is to say, they touch each other externally in this point, point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects their centers together is of course the straight line OM. And this straight line OM, according to this rule 10, must pass through point P, that is their touching point. I repeat again, the straight line OM must pass through their touching point, that is point P. According to this rule 10. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external notch between the semicircle and the quarter circle at point S. The center of this semicircle equals to O. The center of this quarter circle is here at point C. Again, the center of this semicircle is 0.0, and the center of this quarter circle is 0.c. And the straight line that connects the centers together is, of course, the straight line OC. This straight line OC, according to this rule, rule 10, must pass through point S, that is their touching point. Again, the straight line OC must pass through their touching point, that is actually point S. Or OSC is one straight line. According to rule 10, OSC is one straight line. So we join points O and C together by straight line, and according to rule 10, the straight line OC must pass through point S. You can see from the moment that it's very easy to see that indeed the straight line OC passes through point S, that is the touching point of the semicircle with the quarter circle. So if OSC is one straight line, it means that OC equals to OS plus SC. Again, OC must be equal to OS plus SC according to rule 10. So write it down. OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle, that is equals to x over 2. So OS is x over 2 plus SC. SC is the radius of this semicircle, that is equals to x according to our definition. So here SC equals to x. So in total, we actually found out that OC equals to x over 2 plus x. X over 2 plus x is either 1.5x or 3 over 2 times x units in its length. So in conclusion, we found out that OC equals to 3 over 2 times x units in its length. This is line segment OC. That is equals to 3 over 2 times x units in its length. In the next step, I'll copy the right triangle ODC in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle ODC. Here by PT is a version for Pythagoras theorem. Side OD equals to x over 2 units in its length, and side DC equals to 5 units in its length. And we just right now found out that OC, the hypotenuse OC equals to 3 over 2 times x units in its length. So actually, this is the right triangle ODC that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle ODC, OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. OC is 3 over 2 times x, therefore OC squared is 9 over 4 times x squared, and it is equals to OD squared. OD is x over 2, again OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in conclusion, we found out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and 8 quarters x squared equals to x squared over 4 minus x squared over 4 is 0, so we're left only with 25 in this side of the equation. So we found out that x 8 quarters x squared times 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared, and 2x squared equals to 25. Here we divide this equation by 2, and finally you get that x squared equals to 25 over 2. X squared equals to 25 over 2. Here we take a root out of this equation, and finally you get that x equals to the square root of 25, that is 5 over square root of 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again, the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So write it down. The area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? We know that the area of any rectangle equals to the length of the rectangle times the width. The length is AB, that is 5. The width is BC, that is x. So the area of rectangle ABCD is 5x. Minus the area of this semicircle. What is the area of this semicircle? We know that the area of any semicircle equals to pi times the radius of the semicircle squared divided by 2. The radius of this semicircle is x over 2, therefore the area of this semicircle will be equal to pi times x over 2 squared divided by 2. So I write it down. The area of the semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2, minus the area of this quarter circle. The area of this quarter circle, we know that the radius of this quarter circle is x, therefore the area of this quarter circle must be equal to pi x squared over 2. That is minus pi x squared over 2, pi x squared over 4. Again, the area of this quarter circle equals to pi x squared over 4. So the area of the green shape equals to 5x, and we have here pi over 2 times x over 2 squared. X over 2 squared equals to x squared over 4. So in total, the area of the semicircle equals to pi x squared over 2 times 4 minus the area of the semicircle, that is pi x squared over 4. So, so the area of the green shape in total equals to 5x. Here we have pi x squared minus pi x squared over 2 times 4, that is 8. So in total this expression equals to minus pi x squared over 8, and here we have minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. So after we multiply it by 2, we get that this expression will be equal to minus 2 pi x squared over 8. So there of the green shape in total equals to 5x, and here we have minus pi x squared over 8 minus 2 pi x squared over, minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total we should find out the area of the green shape equals to 5x minus 3 pi x squared over 8. But we already found out that x equals to 5 for the square root of 2 units in its length, and x squared equals to 25 over 2. Therefore we can substitute x in this expression by 5 over square root of 2, and we can substitute x squared in this expression by 25 over 2. We do it now, and we get that the area of the green shape equals to 5 times x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total we should find out that the area of the green shape equals to 5 times 5 is 25, therefore in total this expression equals to 25 over square root of 2. And here we have, in the numerator of this expression, we have minus 3 pi times 25, that is minus 75 pi, divided by 8 times 2, that is 16. So in total we should find out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. Or in terms of numbers, the value of this expression in total is equals to 2.95 square units. And that is the answer to the question. Repeat again, I shall find out that the area of this green shape equals to 2.95 square units. We finished with the second question. The next step, we'll summarize the lecture. We start with the first question, of course. Our mission in the first question is to find out the area of this semicircle that is located inside quarter circle A or B. So in the drawing we have quarter circle A or B. We know that the radius of this quarter circle AO equals to 5. And inside this quarter circle we have this semicircle, and again our mission is to find out the area of this semicircle. So in the first step we define the center of this semicircle. This point is point C. Likewise, we define the touching point between the semicircle and the quarter circle. The first touching point between the semicircle and the quarter circle, this point is point F. We define the second touching point between this quarter circle and this semicircle. This point is point G. Likewise, we define the point of tendency of tangent BO with this semicircle. This point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, we define the radius of this semicircle as x. Therefore, the radius CF of this semicircle equals to x, and the radius G of this semicircle also equals to x. So here, in the next step, we join points C and L together by a straight line. CL is of course the radius of this semicircle, that is equals to x. We also join point C and H together by a straight line. CH is also the radius of this semicircle, that is equal to x. So here we can implement rule 1, because why we can implement rule 1? Because we have the radius CL of this semicircle that is equals to x. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. Whenever your radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have also the radius CH of this semicircle that is equals to x. The radius CH is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we created it quadrilateral CHOL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral CHOL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we relate to quadrilateral CHOL as rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the same rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH is also x. So we should find out that quadrilateral CHOL is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square is equal to x units in its length. In the next step, we join points O and C together by straight line. By joining points O and C, we get here the right and associated triangle, triangle CLO. So copy the right triangle CLO in a new page and implement the Pythagoras theorem in this right and associate triangle, triangle CLO. This is the right and associate triangle, triangle CLO that I copy from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle CLO is CO, and therefore the square of the hypotenuse is CO square, and CO square must be equal to CL square plus LO square. CO is the missing side, so we leave it as it is, so CO square equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total CO square equals to x square plus x square, that is 2x square. CO square equals to 2x square. Here we took out of this equation and finally found out that the missing hypotenuse CO is equals to the square root the square root of 2 times x units in its length. Yeah, CO, the length of length CO is equals to the square root of 2 times x units in its length. Point O is the center of the quarter circle. So from this point, that is the center of the quarter circle, point O, we have line segment OC that bisects chord FG. Why line segment OC bisects chord FG? Because of the fact that CF equals to CG equals to x. Each side line segment OC bisects chord FG into two halves. Each half equals to x. CF equals to x and CG equals to x. And whenever you have a line segment that is drawn from the center of the circle and bisect the chord, you can implement rule 7. So I'll repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisect the chord, then the line segment will be also perpendicular to that chord. So in the drawing we have a circle. This is point O, that is at the center of the circle. From the center of the circle, that is to say from this point O, we have line segment OM that bisects chord AB. That is to say MA equals to MB. And because of the fact that line segment that is drawn from the center of the circle, that is to say from point O bisects chord AB, line segment OM will be also perpendicular to AB. That is to say, if OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you have a line segment that is drawn from the center of the circle and bisects the chord, then that line segment will be also perpendicular to that chord. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from this point O, we have line segment OC that bisects chord FG. And therefore, so all the requirements of rule 7 are satisfied, and therefore according to rule 7, line segment OC will be also perpendicular to FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. In the next step, we join points O and F together by straight line. OF is the radius of this quarter circle that is equals to 5 units in its length. In the next step, I copied the right and green triangle CFO in a new page and implemented the Pythagoras theorem in this right green triangle, triangle CFO. So this is the right and green triangle, triangle CFO that I copied from the original drawing. According to the Pythagoras theorem, this right triangle CFO, FO square, that is the square of the hypotenuse, must be equal to FC square plus CO square. Again, FO square equals to FC square plus CO square. FO is 5, therefore FO square is 5 square, that is 25. And it is equals to FC square. FC is x, therefore FC square is x square plus CO square. CO is square root of 2 times x, therefore CO squared is 2x squared. So in total we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So 25 equals to 3x squared. Here we divided this equation by 3 and finally found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of this semicircle? Actually the area of any semicircle equals to pi times the radius of the semicircle squared divided by 2. The radius of this semicircle is x, therefore the area of this semicircle must be equal to pi x squared over 2. And then again the area of this semicircle, that is the area that we are looking for in this question, is equals to pi x squared over 2. So it is pi over 2 times x squared. And we just right now found out that x squared equals to 25 over 3. Therefore we can substitute x squared in this equation by 25 over 3. We did it, and we found out that in total the semicircle equals to pi over 2 times x squared. And x squared is 25 over 3. So in total the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. Okay, so I'm finished with the first question. In the next step, I presented to you the second question, and we solved the second question of this lecture. Our mission in the second question is to find out the area of this ring shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. Again, our mission is to find out the area of this ring shape. First of all, we defined the radius of this quarter circle as x. That is to say, the radius of this quarter circle that is equals to BC is equals to x units in its length according to our definition. We know that all the angles inside the rectangle are right angles. So this angle is a right angle. In addition, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. In addition, according to the sum rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD. But BC equals to x, therefore the opposite side AD must be also equal to x. We defined the center of this semicircle, this point, as point O. We know that AD equals to x. AD is one side of rectangle ABCD, but AD is not only one side of rectangle ABCD, but it is also the diameter of this semicircle. So we know that the diameter of this semicircle, AD equals to x. If the diameter equals to x, the radius must be equal to half of it. That is to say, to x over 2. So the radius OA of this semicircle must be equal to x over 2 units in its length, and the radius OD must be also equal to x over 2 units in its length. So here we actually have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally in this point S. And whenever you have an external notch between two circles, or semicircles, or quarter circles, you can implement Rule 10. So I'll repeat quickly on Rule 10. According to Rule 10, if two circles touch each other externally, then the straight line that connects their circles together passes for their touching point. So in the drawing we have two circles, and they have an external notch between them, and this point P. That is to say, they touch each other externally, this point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects their circles together is of course the straight line OM. So this straight line OM, according to this Rule 10, must pass through point P, that is their touching point. Again, the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this Rule 10. So we can actually implement Rule 10 in our drawing. Why? Because in our drawing we have an external notch between this semicircle and this quarter circle. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the centers together is of course the straight line OC. This straight line OC, according to Rule 10, must pass for their touching point, that is the point S. Again, the straight line OC must pass from point S, that is their touching point. Or OSC is one straight line. Again, OSC is one straight line according to Rule 10. If OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle, that is x over 2, plus SC. SC is the radius of this quarter circle, that is x. So in total, OC equals to x over 2 plus x, that is either 1.5x or 3 over 2 times x units in its length. OC equals to 3 over 2 times x units in its length. This is nice right OC, that is equals to 3 over 2 times x units in its length. In the next step, I covered the right triangle ODC in a new page, and we implemented the Pythagoras theorem on this right triangle ODC. So this is the right triangle ODC that I called from the original drawing. OD equals to x over 2, DC equals to 5, and we just found out that hypotenuse OC equals to 3 over 2 times x units in its length. According to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. OC is 3 over 2 times x, therefore OC squared must be equal to 9 over 4 times x squared, or 9 quarters x squared. and it is equals to all this square. All this x over 2, therefore this square is x squared over 4 plus this is squared. This is 5, therefore this is square is 5 squared, that is 25. So in total we should find out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtracted x squared over 4 from this equation and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. And x squared over 4 minus x squared over 4 is 0, so we left only here is 25. So in conclusion, we actually found out that 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared. So 2x squared equals to 25. Here we divided this equation by 2, and finally found out that x squared equals to 25 over 2. Here we took out of this equation and finally found out that x equals to the square root of 25, that is 5 over the square root of 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again. The area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length of rectangle ABCD is AB, that is 5, the width is BC, that is x. So in total, the area of rectangle ABCD equals to 5x. So again, the area of rectangle ABCD equals to 5x minus the area of this semicircle. What is the area of the semicircle? We know that the area of any semicircle equals to pi times the radius of the semicircle squared divided by 2. The radius of this semicircle is x over 2, therefore the area of this semicircle must be equal to pi times x over 2 squared divided by 2. And again, the area of this semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2, minus the area of this quarter circle. What is the area of this quarter circle? We know that the radius of this quarter circle is x, therefore the area must be equal to pi x squared over 4. And again, minus the area of the quarter circle, that is pi x squared over 4. So the area of the green shape in total equals to 5x, and this expression equals to pi over 2 times x over 2 squared. X over 2 squared is x squared over 4. So in total, this expression equals to pi x squared over 2 times 4. Again, this expression in total equals to pi x squared over 2 times 4 minus pi x squared over 4. So the area of the green shape equals to 5x, and here we have pi x squared over 2 times 4. 2 times 4 is 8, so in total this expression equals to minus pi x squared over 8. And here we have minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. After we multiply it by 2, we got that this expression will be equal to minus 2 pi x squared over 8. So in total, the area of the green shape equals to 5x, and we have here minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x equals to 5 over the square root of 2 units in its length, and x squared equals to 25 over 2. Therefore, we can substitute x in this expression, by 5 over the square root of 2, and we can substitute x squared in this expression by 25 over 2. We did it, and we should found out that 5 and x equals to 5 over the square root of 2 minus 3 pi over 8 times x squared, and x squared equals to 25 over 2. So in total, the area of the green shape equals to 5 times 5, that is 25. So in total, this expression equals to 25 over the square root of 2. And here we have minus 3 pi times 25 over 2. In the numerator of this expression, we have minus 3 pi times 25 is minus 75 pi over 2 times 8 is 16. So in total, this expression equals to minus 75 pi over 16. So in conclusion, we should find out the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the area of this green shape equals to 2.95 square units. Okay, thank you very much.